Jordan Reigelsperger, presenting my capstone project for 909 for Arizona. It's spatial and statistical basketball analysis at the high school level. All right, so advanced analytics in sports really began in the late 70s and the early 80s with Major League Baseball, the Society of American Baseball Research. This movement was kind of made famous in the early 2000s by the Oakland Athletics, general manager Billy Beane, and the movie Moneyball. I don't know if anybody's ever seen that. The NBA, though, was a little bit slower to advance these kind of advanced analytics, mostly because they needed more spatial data. Basketball has many more variables than baseball. If you think of baseball, it's generally a pitcher and a batter. That's, most of the action you're going to get. But NBA, you got 10 different players running around on the floor. They're all guarding different people. They're running different plays. They're switching who they're guarding. So it was really hard for basketball to kind of delve deeper into analytics until about 2010, 2012, the NBA started installing player tracking cameras in all the NBA arenas. And they also put trackers in the balls to start tracking where the ball was moving, where the shots are being attempted from. This really kind of started the NBA analytic evolution. People like Kirk Goldsberry is probably the most famous kind of spatial analysis guy for basketball. Started at Michigan State as an assistant professor for geography, and within a few years, he was the head of analytics for the San Antonio Spurs and Team USA basketball. So some of the tenets of this evolution was less mid-range shots, shots between the three-point line and the paint, and many more three-point shots, especially from the corners, called corner threes. So for this project, I just wanted to see if these principles were making it down to the high school level, and if the same kind of analysis that Goldsberry provided to NBA teams would be useful for high school. In this chart that he's holding, I actually performed that same analysis for this high school team, so you'll see it later on. The methodology, first of all, I just gathered and entered the data. There'll be more about data on the next slide. Then I grouped the subjects into my analytic groups, which included each individual player, the top three used lineups, and the team as a whole, as well as the opponents. Then I selected the statistical metrics and the spatial metrics I wanted to analyze. Then I created visualizations and then analyzed the results and came up with some conclusions. So going back to the data, all the data was point data. I'm going to be calling them events. All the data was derived from manual review of game tape. So I sat down and watched all the game tape from 5 games of the last season, the 2020-2021 season, and then manually entered every event. I ended up with over 1,000 discrete events, individual events, and each event had about 13 fields of amplifying information filled out, ranging from like who the player was associated with the event, like if it was a shot, how much was it worth, did they make it, what kind of defense was being played, some other things. So all in all, I had over 1,000 data points and over 13,000 fields I filled out manually. And that was the main data challenge. It was very time consuming. Spent probably 50 or 60 hours just watching tape and entering events into ARC. The other data challenge is due to COVID this last season, a lot of the times I couldn't have people in the stands videotaping the games. So for this study, it's just 5 games of the 20-game season. So it's a pretty small sample size, 25% of the season. There's just an overview of the analysis. They're going to be going over. Analysis 1 and 2 are statistical measures, and analysis 3, 4, 5, and 6 are all spatial measures. So analysis 1 is true shooting. True shooting is basically how effective a player is at putting the ball in the basket, how good they are at scoring and shooting the ball. It accounts for free throws, 2-point shots, and 3-point shots. It makes it different from field goal percentage, which is just a raw, how many did you make, how many did you miss. The top player results for these were number 3, number 23, and the top lineup was number 40. So it's important to kind of keep these in mind because these statistical references are going to provide some more context for the spatial metrics and to remember these players in this, and especially lineup 40. So lineup 40, as you can see, was the highest in true shooting percentage, but it was the 3rd most used lineup. Lineup 1, the worst lineup for true shooting, was actually the starting lineup. And by far had the most data points, but it performed the poorest in true shooting. Also of note is number 3 and number 23 were on are included in lineup 40 and not in lineup 1. So there's kind of a relationship between those two players and higher offensive efficiency. Next, I did offensive and defensive rating. Offensive rating is how effective a team is at scoring the basketball, and defensive rating is how effective they are at keeping the other team from scoring the basketball. So you want a high offensive rating and a low defensive rating. Across the 5 games, game 1 was the only one with a positive net differential, and that's also the only game they won out of this sample size. They were 1-4 in total. They had a negative net differential across the entire sample size, and once again, lineup 40 was the only one with a positive differential. And you can kind of see the relationship between offensive rating and true shooting between lineup 40 because it was the highest in true shooting and the highest in offensive rating. All right, now to get to the spatial metrics, this is going to be field goal percent per zone. So I divided the court into 11 discrete zones and basically just calculated the field goal percentage from each of these zones to see any spatial patterns I could find. So they only had one field goal or one zone above 40% field goal percentage, and that was in the paint. You can see it in yellow on the right-hand side if you're looking down offensively. This kind of correlates to every player on the team was right-handed, and this is generally where right-handed layups are going to be shot from. So, I mean, layups are the most efficient shot in basketball, especially with your primary hand, and this is where they perform the best. You can see, going back to kind of the NBA analytic evolution thing, that there's a very low percentage of corner three-point shots here across the total, and they didn't shoot very well from those. And there's also still a lot of mid-range shots being taken, which is another signal that they like the new strategies and trends and patterns from the NBA haven't really made it down to high school, at least for this team. These are the lineups, field goal percentage per zone. You see kind of the same pattern, relatively well in the paint near the basket and pretty poor everywhere else. Lineup 40 only shot 3-point attempts from one of the zones, one of the 4 3-point zones, but they also had the highest offensive efficiency. So, you know, more layups near the basket, higher efficiency shots. So that's kind of the pattern we're seeing here. Next, I did point per shot per zone. This is kind of similar to field goal percent per zone, but here we're just substituting point per shot. So point per shot is just how efficient or how many expected points you can expect to get from each shot. So if you shoot 2 2-point shots and you make 1, you score 2 total points with 2 shot attempts. You just divide those 2 numbers and you're going to get 1. Same thing if you went 1 for 3 from a 3-point zone. Anything above 1 is going to be considered efficient, and anything below 1 is going to be considered inefficient. Next slide. And we're going to see the same kind of trends on the for point per shot per zone. Relatively well inside the paint, poor outside shooting, especially from 3. There's some little small sample outliers from the 3-point range, like lineup 1 has 1 green zone from the 3-point area, 1 efficient zone, but it's a relatively small sample. Same with lineup 13 in the left corner, 3. I think they shot 1 for 2 from there, so small sample size. Next, I did spread and range percentage. This is that analysis that Kirk Goldsberry had on, I think it was the second slide. So the court's divided into scoring cells. In my case, I had roughly 1,350 scoring cells in that offensive half court. And it's just tracking how many of these scoring cells players have attempted a field goal from. And this gives you a metric on how varied a player's shooting range is. Right? And then range percentage, you take those scoring cells, the spread percentage, and you find out how many of those cells they had over 1 point per shot. So, and how many cells somebody's efficient in. So it gives you like a wide breadth of this player's good at shooting from multiple locations on the court. Spread and range does have a kind of a downfall though. It's just, it can be skewed by players that shoot a lot of field goals because they're going to have more scoring cells occupied than players that don't. But that doesn't, you know, obviously make them more efficient just because they shot more shots. So that is a problem with spread and range, to keep that in mind. And you can see the spread leaders are number 12, number 1, and number 11. Same with the range percentage, but these are also the people or the players that attempted the most field goals. And if you remember from true shooting, player 3 and 23 were the most efficient on true shooting, but they're not on here at all because they have low scoring cell output with number 3 having 13 scoring cells and number 23 having 12 compared to, you know, 51 for player 12. Here's the results. You can kind of see the same patterns on all these graphics. A lot of, not a lot, but majority of their efficient shots are going to be near the paint, represented in blue, and everywhere else is going to be pretty red and inefficient across every player, all the lineups in the team as a whole. Next, I ran Ripley's K on the point data. For this analysis, I wanted to see if there's any relationship between clustering, significant clustering or dispersion, and offensive rating. I expected all the shots to be like very clustered because the shots are going to be clustered near the basket. Teams run plays to get shots in specific areas. So the fact that everything was very statistically significant on clustering wasn't a surprise, but I couldn't really identify any relationship between clustering and offensive rating. I think this is due to there's no metric or no way to kind of tell shooting ability just from running Ripley's K, because you can have a bunch of clustered shots, but if the player just doesn't make them, that's not going to show up in offensive rating. And you can have dispersed shots that teams or players make a ton of, so it'll kind of skew the results. So I don't think Ripley's K was really shed a light on anything here, unfortunately, unless there's some way to like incorporate shooting ability into the metric. Excellent. All right, so conclusion, we went over efficiency metrics and spatial metrics like true shooting, offensive rating, spread and range percentage, field goal percent by zone. I didn't see any evidence of the analytic revolution in this high school team, at least. There was a low number of corner three-point shots with a high number of mid-range shots still. But this could be due just to player skill and strategy. Because even if this high school team, they proved to be a pretty poor outside shooting team, even if they ran the same plays, the same strategies as NBA teams, looking for corner three-point shots, looking for three-point shots, if they don't make them, they're not going to be efficient. So it's kind of like a chicken or the egg thing where you can run the plays, but they might not be efficient. And they might be better off just running inefficient plays that their players are actually better at. That's my presentation. Open it up to the floor for questions and feedback.